Okay, welcome to another video on triple integrals. In this video, we're going to be developing the notion of cylindrical coordinates. So to begin with, let's talk about a little bit of what we have covered so far. So we know that if we have some sort of rectangular kind of region on the xy plane, we can normally just solve this by direct integration. So if we have something like a triple integral, and then we have some region on the xy plane that sort of defines that that constraint for the z-axis, then we can perform an integration of the following sort, and we can just use Cartesian coordinates if the function is simple enough to use. So let's say we have some region E. Now, obviously, this only works for rectangular kind of regions, and we saw that we can also do sort of very basic triangle region. But what happens if we have something like a circular region on the xy plane? Then things become a little bit more complicated, because obviously there's gonna be a lot of relationships between x and y that are gonna depend on either square root of some function like this, or we're gonna have more complicated expressions. And you can imagine that if the function of 3 variables is complicated enough in itself, then this is just going to become a mess. So what we can do is we can develop another coordinate system, which we will call cylindrical coordinates, that hopefully will make this a lot easier for us to do. So what are cylindrical coordinates? Well, remember that when we developed the concept of polar coordinates, we took a circle, and then basically we just draw an infinitesimal element that had the following dimensions. So we basically treated it as a little rectangle that was a little bit deformed. So basically we said, let's say this is the r, and the arc length, we know that it's going to be r times d theta, because r is just going to be the distance from the origin of, or the center of the circle, to that point along the circumference. So this is going to be our element. And basically we said that the area, or the infinitesimal area contained by that little element, was r d theta. So that was what we developed with polar coordinates. Now, what happens when we want to take this to the third dimension? Let's say we have our xyz space here, and let's say we have some sort of circular region along the xy plane, but now this is going to extend all the way up. So remember, now this is going to be constraining whatever we try to integrate along the z-axis as well. So this is going to be like a cylinder that goes to infinity in both directions. So what we're going to do now is we're going to take a little slice. So we're going to take the same kind of area that we did already. So I'm actually going to draw this in a different color so you can see it better. So we're going to take this little infinitesimal slice, but now it is going to have a height. Because remember, we're now taking that circular area and we're extending it to infinity in both directions, and we're forming a cylinder. So that's basically all a cylinder is. It is just a circular area that extends along a specific length. So now instead of having an element of area, we're going to have an element of volume. And the relationships are going to be the same. We know that for any cylinder shape, we can do the calculation for the volume as follows. So volume of a cylinder is just the area times the height. And the area is just going to be whatever area we have. In this case, our area is going to be dA, which is the exact same expression we have here. So let's just make dV. And the height is just going to be a very small change in z. So this is going to be dA dz. So how can we write this now? Well, this is going to be quite simple. We can write dz. So I'm just going to write it at the front, because remember, usually with functions of 3 variables, we want to integrate with respect to z first. So we're going to have dz, and now here we're going to have r d theta. And because we can usually rearrange terms, we can have the following relationship for the volume element. So this is going to become r dz dr d theta. So this is our volume element for cylindrical coordinates. Now, how do we derive the actual parametric relations for the cylindrical coordinates? Well, you can imagine that x and y are going to be the same along both directions along z. This is just going to be constant. So we know from polar coordinates that x equals to r cosine of theta and y equals to r sine of theta. So this is something that we derived already when we were solving double integrals. So this is going to remain unchanged. We're going to have the exact same parametric equations in cylindrical coordinates. So r cosine theta here, y equals to r sine theta. And then what do you think z is going to be in parametric form? Are we actually changing anything in z? No, because we are just extending this circular area along the z-axis. So z is just going to be itself. So there's no parametric equation required for z in terms of those two other variables. So this is going to be our parametrization in cylindrical coordinates. And obviously we can also establish the relationship x squared plus y squared equals to r squared. So these are basically our important relationships, the ones that we will be using to solve a triple integrals using cylindrical coordinates. Alright, so now that we have established that, let's solve a very simple example. So let's suppose that we have the following integral. So example, we have the integral 0, 1, 0, 1 minus x squared, and then we're going to have 0, 2xy, and then our function is going to be x squared plus y squared, dz, dy, dx. Now this looks a little bit complicated, and you might think, well, if we try to integrate this using Cartesian coordinates, well, the first integration is very easy. We just multiply each of these by z, and then we just replace this by that. So we're going to get a polynomial kind of expression afterwards. But what happens when you integrate with respect to y? You're going to get this very ugly expression in it. And then this is going to result in a product of some polynomial of x with some expressions involving some root of this expression here. So it's going to get quite ugly after the second step. So what we can do is we can try to see if there are any relations here that sort of relate back to polar or cylindrical coordinates, and we can see that, well, we can substitute this by r squared, so that would simplify that greatly. And this expression right here can also be related to this expression here. So having seen that in this integral, we can begin to make that substitution. So what is the first thing we need to do when changing coordinates in a triple integral? We need to look at the dy dx part of it. So remember that we're integrating with respect to z first, but in general we need to define the region on the xy plane first before we define the region along the z plane. So if we take this little portion here, this is going to give us the limits for both x and y. So we're going to have the following. So those are the limits in x and y. And from this we can actually draw a region on the xy plane. So what is this going to be? Well, we're going to go from 0 to 1 here along the x-axis, and then y is going to go from 0, so that's going to be just the x-axis. And it's going to go up to this semicircle kind of function. So what is going to be the radius of this? Well, it should be 1, because if we put x equal to 0 here, that just gives us 1. So we're going to have this quarter circle region here. So this is going to be a region D. So that's essentially the region of integration we have with respect to x and y in this integral. Now what we can do is, since this is a quarter circle, we can use polar coordinates, as we have done before, to actually change those limits of integration. So the first thing we can do is look at the angle theta. So we're basically starting at the x-axis on this side, on the first quadrant, and we're basically moving up to the y-axis. So that's basically covering a full quadrant, which means that theta is going to go from 0 to pi on 2. And then r is going to go from 0, because essentially the radius is constant. It is just being rotated by this angle. So the radius is going to go from 0 to 1. So now we established those limits. Now what about z? Well, now that we have established what the region along the xy plane is, we can actually draw the limits for z. So all we need to do is we use the parametric equations we have here to substitute for those limits on z. So z is going to go from 0 to 2r squared. So remember that we have r cosine and r sine. So 2r squared cosine theta sine theta. So those are our three limits. Now we can perform that change into the new coordinate system. So let's do that. We're going to have the integral. So just for the sake of argument, I am going to integrate in this same order. So we're going to get started with z, which is the one that is dependent on a function of the other two variables. Then we're going to integrate with respect to r, and then we're going to integrate with respect to theta. So let's do just that. So we're going to have 0 to pi on 2, then 0, 1, and then 0, 2r squared cosine theta sine theta. And then here we're going to have r squared. And now we're going to replace this by the element of volume dv in cylindrical coordinates. So remember, this has an r integrated into it. So we're going to have r squared times r. And then we're going to have dz dr d theta. So this is just going to become r cubed. Now this is going to be equal to 0 pi on 2, 0, 1. And now we're going to have the following. So we're going to integrate r cubed with respect to z. So that's z r cubed from 0 to 2r squared cosine of theta sine theta. And then dr d theta. And now with this, what we're going to do is we're going to write 0 pi on 2, 0, 1. We're going to substitute this into z. So this is going to become, so I'm going to put the 2 outside. This r squared is going to multiply that r cubed, so that's going to become r to the power 5. And then we're going to have this element, cosine theta sine theta. And we're going to integrate with respect to r now. So we're going to have r to the power of 6 when we integrate this over 6. So that's going to be 1 on 3 outside the integral. So r to the power of 6 cosine theta sine theta. And now we're going to integrate from 0 to 1. And now d theta. And then this is going to become 1 over 3. 0 pi on 2 cosine theta sine theta d theta. And now if you remember the rules of integration, you can use integration by substitution here. So basically just make u a new variable u equal to sine theta, such that the derivative or the differential du is equal to cosine theta times d theta. And that way you can perform the simple integration. So once we do that, we're going to have the following. We're going to have 1 over 6, so that should be a 6 here, sine squared theta from 0 to pi on 2. And what's this going to be equal to? Well, we know that when sine theta, when theta is equal to pi on 2, basically sine is equal to 1. And when theta is 0, sine is just 0. So this is just going to be 1 over 6. So the final value for integral is just going to be 1 over 6. So that's a really nice result. Very clean, very exact. And now what we can say about this is that cylindrical coordinates work for when we have a region on the xy plane that is described by some sort of circle, or it can be anything that can be expressed in terms of polar coordinates. So it's a really, really nice kind of simplification that can help us with really complicated integrals like this one. And in the next video, we're going to explore another coordinate system called spherical coordinates, which has a lot of similarities with this and can help us solve certain integrals that become a lot more complicated than this one.